All right, let's get started. Today we are going to talk about binary search. Firstly, course logistics. Homework 4 was due today and homework 5 was out today. And regarding midterm, the coverage is from Python primer to sorting. And you could refer to lecture slides, the lecture code and homework problems. And the problem types are going to be as follows. We are going to have 3 types of problems. The first one is WWPP, what will Python print? That is the first type of problems. And similar to the PPP exercises we've dealt with in classes, there are going to be coding problems. And also there are going to be some short answer or multiple choice questions. All right, so these are some information about midterm. So regarding midterm, is there any questions? And it's going to last 2 hours. All right. So if you have any questions, please ask away. And next week on Thursday, we're going to have midterm review. It is an optional lecture. You don't have to attend it. You can choose to attend the class or not. And I'll accept questions in Korean regarding lecture materials, like the lecture slides, lecture codes, or yeah. And regarding homework problems, you can attend TA office hours. TAs could answer your questions regarding homework problems. All right. So to now, is there any questions regarding course logistics? Okay, cool. Let's move on. Firstly, we are going to have a look at the applications of stacks and queues. In the last lecture, I gave you one PPP exercise left, and we're going to solve this problem first, and then gonna discuss today's main topic, which is binary search. All right. So this was the problem we left in the last class. So what we want to do is find the number of islands in this grid, 2D grid array. So the strategy is like this. We scan through all the items inside this grid. And when we encounter one, then from here, we're going to inspect the neighboring items. So in this case, the neighboring items going to be this one and this one. All right. And from this point, we move all the way up to we reach water. So we are going to start from here and go to this point and stop at this point because there is water on the right side. However, we can go further down because there is no water but ground. So we are going to travel inside this land and mark all these ones zeros. And after we've done that, we're going to say, oh, we found one ground. So it is like we're finding all the items connected to this one, right? So we're going to group ones. And as I told you before, we can solve this problem in 2 ways. The first one is using stack, and the second one is using queues, all right? So firstly, let's solve this problem using queue as stack. And then we're going to solve this problem with queue, right? Okay, so we're going to define a count variable like this. And we're going to define a stack, but here we're going to use a list, Python list as our stack, all right? And what we're going to do is inspect all the items inside this 2D grid. So for I in range len grid, this is the first dimension. And for j in range len grid 0. So this is going to be the dimension in the x direction, and this is going to be dimension in the y direction, all right? Actually, this one is x and this one is y directions, all right? And what we are going to do is, if grid I and j equals 1, we found one island, one possible island, right? And what we are going to do is push this item into our stack, I and j, like this, all right? And while this stack contains some items, we're going to pop some items from stack like this. And we're going to make this position 0. All right. So let's say we came over here and we're going to mark this part as 0 because we already inspected this part. And because we are not going to inspect water parts, it is okay to mark this one as 0, all right? And we're going to find all the neighbors of this position and mark them as 0 as well, all right? So that is the first step. Mark the first position 0. And what we are going to do is we are going to look at the neighboring items. So if grid -1 and underbar j equals 1, then we're going to append this position into our stack. And in the next iteration, it is going to look up this item, and find its neighbor. So let's say if this one was first put into our stack, and next we are going to inspect this one, and this one's neighbor, which is this one, will be put into our stack. In this way, we can inspect all the items connected to each other, all right? So that is the strategy. So we saw the item at the bottom, and other things are similar. So the next thing we're going to do is upward neighbor and downward neighbor, like this. However, what we're going to do is return count. However, there is one caution you need to be cautious about, you need to be careful about, is sometimes I could be 0. In such a case, we cannot inspect I -1 because this index is going to be -1. And that is not what we want. So we are going to add another condition like this. I has to be larger than 0. Then we can inspect this neighbor, all right? And in this case, we cannot inspect outside of this grid. So we need to add this condition. All right, we do the similar thing for j. Like this. This has to be grid 0 and j has to be smaller than this one. All right. So this is our solution to solve this problem with stack. So up to this point, is there any questions regarding this solution? All right, I think everything is clear. And the next solution is using Q, right? Here we are going to do the similar thing. We first define a variable to count the number of islands, all right? So we do a similar thing like this, right? And if grid I and j equals 1, what we are going to do is mark this one as 0 first. And then in our queue, we are going to put I and j like this. And here we can use the default queue offered by Python like this. And this is actually in queue, what we defined. However, Python uses different name. They use put instead of in queue, all right? So we put this position into this queue, and we are going to search all the neighbors connected to this I and j, right? So while queue is not empty, in our implementation, we defined a method called size, but in the case of default queue offered by Python interpreter, it uses queueSize method, all right? And we're going to retrieve the item inside this queue. This one is dequeue. This get method corresponds to dequeue. And what we are going to do is for I and for j in this case, we can simplify the iteration like this. So let's check if underbar I is in the valid range. And we also need to check grid I and j should equal 1 like this. Then we're going to mark this part as 0, and we're going to put this position into our queue and continue to inspect the neighbors of this position after the next iteration, all right? And after this while, we're going to +1 to the count, and we're going to return count like this, right? So this one is very similar to the solution using stack, all right? So this is 2 ways of solving this problem. So regarding this problem, is there any question? All right, cool. If you can solve this problem in 3 hours, then that is okay. Generally, companies give you like 2 to 3 hours to solve this one problem. So if you can figure out how to solve this problem in 2 or 3 hours, then that is wonderful. All right. So that was small recap about last class. And let's continue on our today's topic, that is searching. Searching is a process of looking up data. For example, we can look up a person in the telephone book. Nowadays, we don't use telephone book, but we just search on our cell phone, smartphone. Or you can search for the meaning of a word in a dictionary. Nowadays, we don't use dictionary, but we use internet web. However, computer has to do the job for us. So we need to implement these algorithms to search something. And Python lists have a method called index. And this returns the index of the first element that is equal to X, all right? And if the elements of the list in this list, given list, are in no known order, we can only use sequential search. It is also called linear search. This is the implementation of linear search. This is very simple. A is the given list. And from this list, we want to find an item whose value equals X. In this case, what we can do is just iterate over all the items inside this list A. So we are going to make a loop that iterates over len A. And we inspect each item inside this A and check if this value equals X. And if this value is equal to X, then we return the index I. And after all this iteration, if we haven't found any item that matches X, then we are going to raise value error. We'll say there is no item that matches X. All right, so this is very simple. And this is linear search. And in general, the complexity of linear search is O(n), because we need to check all the items inside this list. And n is the length of this list A. And can you do better than this? And it is often possible to improve this in practice. We can keep often needed elements at the front of the list. In this case, the best case is going to be O(1), because the item we are looking for is at the front of the list. How can you do this? We are going to talk about this after midterm, all right? And what about search in sorted cases? In the previous case, we assumed that the items inside this list is not sorted, not in order. However, let's say a list contains items that are in the order of non-decreasing sequence of integers. In such case, we can stop as soon as we find the item we're looking for. So if the items inside this list A are sorted or are in order, then we just look for the items as before. But if we found the position of the items that are larger than X, then we just return the index. Otherwise, we return length A. So why don't we raise an value error as before? In this sorted linear search, what we return is possible position where this item should be or can be inserted. All right. So if this item of interest is the largest one, then we are going to append this one at the end of this list. So that's the reason why we return the length of this list. All right. So This is today's main topic, binary search. What is a binary search? In the cases where the data of a list is sorted or in order, like non-decreasing order, we compare the item of interest with the middle element. And search, if the middle element is what we are looking for, then we just stop there. Otherwise, we search in the left half or the right half. If the value of interest, x, is larger than the middle value, then we're going to look up, search in the right half side. If the value is smaller than this middle element, then we're going to continue to search in the left half, all right? So that is the strategy. It is one of the most intuitive and the most intuitive implementation is using recursion. And as I told you before, we are making binary decision in every step. And that is the reason why we call this one as binary search, all right? And this is the picture of binary search. So we first check the middle value. And what we are looking for is 37. And because this one is smaller than the value we're looking for, we just go to the right half. And in the middle, we also make another decision. And 41 is larger than the middle value. 41 is larger than 37. So we look up the left half, right? So in this case, we first go to the middle and go to the right half and go to the left half and go to the right half. Then we found the value. And it takes really small steps to find the value we are looking for. However, sequential search takes much more time than binary search. And this is binary search in average cases. And in the best case, if the value we are looking for in the middle, then it takes just one step, right? And in the worst case, if the value we are looking for is at the front, then we are going to spend 4 steps. However, in sequential search, it takes only 1 step, all right? So this is binary search in the worst case. And we are going to implement binary search from now on. However, before we implement binary search, I want to talk about one fun fact about binary search. The binary search was first published in 1947. And the first implementation without any bug did not appear until 1962. So after like about 20 years, there had been no implementation without any bugs. In an experiment, professional programmers were given ample time, enough time to implement this binary search. And only 10% of them could get this small program right. And when you actually see the code, this binary search is very simple. However, there are some tricky points. So it is very hard to not make any mistakes. However, nowadays, everyone knows how to implement it in the right way, in the correct way. So don't worry about that. All right, let's implement this binary search together. So up to this point, is there any question? Okay, cool. The idea is very simple. And let's implement this one with recursion. All right, that is our first approach. We are going to have two arguments. The first one is the list, and the second one is the item of interest we are looking for. And we are going to define another function, find recursive, that searches through all the items inside this list. And the reason why we are using different name here is going to be clear after we define find recursive. So here we're going to give 4 arguments. The first one is the list, and the second one is the item of interest. And the third and fourth are the positions we are going to search for. So here, low boundary, and J is going to be high boundary. So at the first time we are calling this function, the low boundary is 0. Apparently it is the front or start of a list. And this one is the end or back of this list. All right. So at the first time we're calling this function, we're inspecting all the items from the start or from the front to the end or to the back. All right. And let's see how we can implement this one. The base case is if J is smaller than I, where the low boundary becomes larger than the high boundary, then we are going to return I. And if this does not happen, we're going to find the middle point like this. And as I told you before, if this mid value is smaller than X, then what we are going to do is find recursive AX mid plus 1 and J, all right? Because X is larger than the middle value, we're going to look up the right half, all right? Otherwise, we're going to return find recursive AX, and we're going to see the left half side like this, all right? So this is binary search. It is very simple to implement, all right? And in the class slides, I told you about linear search or sorted linear search like this. And let's compare performance of these 3 methods. So this is how we are going to compare the performance. We are going to make a list, which is this length, huge list. And we're going to print some items like this. And we're going to find the position or the index of this item, a random item, L. And let's see how this can perform, all right? By the way, Python search looks like this. So I'll copy this code here. So Python search is default search algorithm. And let's see how big the performance difference is. So we make a list of 1 million, length of 1 million. And Python search takes like 15 seconds. We haven't yet implemented the binary search iterative. And binary search takes like 6 microseconds, while sorted list or linear search takes much longer time, all right? So this is the performance difference. And I would like to give you one PPP exercise. That is, can you convert this binary search into iterative one? So your job is convert this binary search, which is defined as recursive function, and turn this function into iterative one. Before you solve this problem, please send me PPP message and take some time and solve this problem. All right, thank you for sharing your answers. Most of you who sent your answers got the right answer. And let's solve this problem together. First, we are going to initialize I and j. At the first time, I equals 0. So we are going to say I is 0. And j is this one. Then a minus 1, like this. And what we are going to do is, before we reach this condition, we need to do this operation again and again, all right? So we are going to negate this condition that is going to be while I is smaller than j, all right? So before we meet this condition, we're going to do this job again and again. So we're going to copy this code because we're going to do this one and check if a mid is smaller than x, like this. So we are using this condition, the same condition here and here. So in that case, what we do is change I as mid plus 1, else we put mid minus 1 to j, all right? And then we return I. So this is how we convert this recursive function into iterative binary search, like this, all right? I think everyone is getting the right answer. Sometimes you put another condition like a mid equals x, you can just return mid, right? So that is also okay. All right, so that was our binary search. So binary search itself is very straightforward and quite easy to understand. And from now on, we're going to solve some PPP exercises together and see how we can apply binary search into practical in some practical questions. The first question, the PPP problem, is implementing this PAL. So this PAL evaluates the x to the power of n, all right? So 2 to the power of 10 is going to be 1024. And one caution here is you need to be able to calculate for minus powers like this, all right? So if you do not support minus powers, then it is pretty easy and simple to solve. However, think about this. How can you support minus powers? As usual, send me some PPP message and solve this problem. I'll give you one more minute. All right, let's solve this problem together. This one is from Hagen. There are also other solutions. However, Hagen's solution was the most efficient one. If you use iteration, like result equals 1, and while I smaller than n result times x blah 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 blah. This one takes complexity O(n). However, because we learned binary search, we're going to divide this problem into 2 parts and solve this one more efficiently. Okay, let's see how we can do this. First, we're going to check if n is equal to 0. In such a case, we're going to return 1. And if n equals 1, then we just return the value we receive. All right, so this is the first 2 special cases. And if n is smaller than 0, what we are going to do is return 1 divided by pow x minus n, like this. So this is how we deal with n, which is negative n. And another thing we are going to do is divide this pow into 2 parts, like this, right? And if n is an even number, then we return div times div. Else, this is when n is odd. Return div times x, like this, right? So this solution works in O log n, right? Which is the binary search complexity. So regarding this solution, do you have any questions? The problem description was not clear. I needed to notify that your solution has to be O log n. All right. If there is no question, let's move on to our second problem. Our second problem is defining a custom square root function. This one is from MSN VMware. What we want to do is find the square root of x. However, we are going to return an integer, and we are going to truncate the decimal digits. So in the case of 4, the square root is going to be 2. However, in the case of 8, this function returns the same value 2 because the actual is 2.8 blah, blah, blah. So we are going to truncate the decimal parts, right? So in the case of 16, it returns 4. In the case of 24, it's 4 point blah, blah, blah. So we are truncating the decimal parts. So we're returning 4. Send me a PPP message and take some time and solve this problem. And your solution has to be complexity O log n. All right, let's solve this problem together. Thank you for sharing your answers. This one is from one of students. This is a linear search. So we start from 1 and increment 1 and 2 like this. And once m times m squared is larger than x, we stop this iteration and return n. This one is linear search. And what we want to do in this class is binary search. I think Hanjun and Hoyok's solutions are similar to the one I got. We are going to search from low and high like this. So we initialize the low point as 0 and high point as x. And while low is smaller than high, we're going to find the midpoint, which is going to be low plus high minus low divided by 2. And we check if mid times mid is larger than x. We're going to set high as mid minus 1. Else if mid times mid is smaller than x, we're going to set low as mid plus 1, like this. Else, we return mid, because mid times mid equals x, that is the square of x, all right? And after we finish this iteration, we return high, all right? So this is binary search of looking for square root. So this is very similar to the binary search we implemented above here. All right, so we are using the iterative one. And here I want to make another note that let's see how this is working. So as you can see here, a recursive binary search takes a little more than the binary search iterative. And can you guess why? We haven't analyzed the time complexity of binary search, but it is O log n, and is the length of the list. However, this log n is very fast and very efficient. However large number is put into this log, it's going to be very, very small, right? And the thing is, the computation it takes is very small. However, in the case of recursion, it entails function calls. So we need to create and delete function stacks. And this takes additional times. However, in the case of iteration, just one function call, so it does not take additional times. So that is the reason why binary search iterative is much faster than quite faster than binary search recursive. Both are very fast. However, iterative binary search is even faster. And when we actually run this part, you can see there are many function calls here. You can see how many function calls are there in our program. So in the case of binary search recursive, there are quite a lot of function calls, all right? So that is one note. The last question I want to give you is some special search. In this case, the nums, the number of lists, are rotated. In this case, it was originally 0, 1, 2, 4, 5, 6, 7. However, it is rotated from here. So let's say this position is pivot. So what we are receiving is not just ascending order list, but ascending order list that is rotated. And we want to find 0 from this list. And we want to take just O log n. That is our target. Right? So in this case, if there is no item inside this list, then we're going to return -1. Right? Can you think about how to solve this problem? This one is quite difficult problem, and you can solve this problem at home. But I would like to give you how you can solve this problem. There are two approaches to solve this problem, to tackle this problem. The first approach is modify the basic binary search. So that is the first one. Here, what I mean by modifying the basic binary search is, in the case of binary search, we thought about where we need to look at after this iteration. So in this iteration, we are looking at midpoint and comparing some values with this midpoint. We decide we search in the left half or in the right half. So the first approach is you modify the basic binary search. And at this point, you need to find some conditions so that you can decide where we search, in the left half or in the right half. So that is the first approach. And the second approach is much more intuitive. The first one is, in this second approach, we're going to tackle this problem in 2 steps. The first step, step 1, we find the pivot. So we say, where is the rotating position? So from this part, these values are ascending order. And up to this point, these values are in ascending order. So that is the first thing we're going to do in the step 1. And step 2, conduct binary search. So we make this order, and we get this order right, and then conduct binary search. And we're going to find the pivot using binary search, and conduct binary search takes log n, and this also takes big O log n. So these two combined together is also log n. All right. And first approach takes just 1 log n. And this one is 2O log n. All right. So this one is 2 times faster than this one. But because log n is anyway faster than any other algorithms, it doesn't really matter. So there are 2 approaches. And think about this. If you can solve this problem in like 2 hours, then that is very good performance. All right. So let's call it a day. And if you have any questions, you can leave here. So you can stay here. Otherwise, you can leave now. Thank you for your participation.